I will do a review of section 2, what I said last week, and I will probably try to finish section 2 today, but I will not start section 3. And okay, because I know that last week we didn't have class, and then most of you have already forgotten most of it, so everybody was in Chuseok. And so what were we talking about? So we were talking about different ways and different algorithms regarding searching. And searching means some type of procedures which operate on an array of some data type and some element or one or two extra elements, and then return certain features like whether the element is in the array and what position or between which elements it is and things like that. Okay, so we had different algorithms, and we were consider them with regard to this characteristics. So we were described what the algorithm was supposed to. So this is specification. Then we agreed on some way of how to count primitive operations. Then we talked about design. So I said that design are the ideas that you need to develop how to efficiently solve the task of the algorithm. And then there is analysis, which is correctness and complexity. And in certain cases, we can prove that the algorithm is optimal. Okay, so and then we were talking about the basic search, which was find an element in an array without any conditions. And we said that the algorithm is simply you have to go through the array from one end to the other and test whether the element is there. And okay, and we said that okay, this is not difficult to see that this is correct, and that the runtime is linear, and that we argue that there is no better way. Okay, for a general array, there is no better way of looking for an element. In you have to use linear time algorithm. And then we talked about neighbor search, which is if you are given an array of some data type with an ordering relation. We are not assuming that this is ordered for the time being. And neighbor search was you have to find an index n such that a given element y is between xn and xn plus 1. Okay, and again, the algorithm is this algorithm that we used here is pretty straightforward. So and again, this runtime is linear, and we said also that we put this artificially this element x capital N plus 1 equal to infinity on the right and x0 is equal to minus infinity on the left, so that there is always an n. Okay? And we remarked before that this n is not unique. So I think I mean, I'm sorry, I have a little bit of, it's not very smooth the way that I can get to questions that you put in the chat, but I see the question sometimes and I try to answer. So one question in the chat from, I think last time, even if it was almost 2 weeks ago, was what happens if xn is bigger than xn plus 1? Okay, and in this situation, okay, we have not assumed that this is ordered, so this is very well possible, and the answer is this is okay. Simply n will never be output as a result for whatever y. Obviously, if for some y this is satisfied, then xn is less than xn plus 1. So if xn is bigger than n plus 1, there will be no y which satisfies this. So for whatever y, this n will never be output. Okay, but you must be careful that if this is not ordered, then this n is also not unique. So this means for the same y, there could be different n's which correct. Okay? And this algorithm outputs one of these n. So this is always something that I said you have to consider when you run an algorithm. Is the output supposed to be unique? So you can have two algorithms which output different things, and the algorithm can still be correct. So uh, and but I said then if this is ordered, then you can then n is unique. Okay. So and then we went to this improved runtime for searching in an ordered array. Okay, so now we assume not only there is an ordering relation, but also assume that the array is ordered. Again, we put artificially right element to infinity, left element to minus infinity, so that this searching result always exists. And then we are looking for essentially the same thing as here. Okay, so it's just written a different way. So simply put n plus 1 in the neighbor search to be equal to r in here. Okay, and so essentially we're looking for the same sort of output. Okay, we're looking for the index so that a given element y is between the rth element and the r minus first. Okay, and so then we said that we can do better. Okay, so if the array is ordered, we can always test with the middle element. Okay, and then we can restrict the right end and the left end to the middle element depending on whether how the middle element compares to y. Okay, and in this way we can shorten our interval by a factor of 2 essentially every time, and this is why you get a logarithmic growth. And now for later reference, let me call this here. Oops. So let me call this here bean search. Okay, so I will refer to I will need this algorithm later. So let me refer this to this algorithm as bean search. And again, the output of the input of this algorithm is x and an array of elements of some data type x and an element y. Okay, and now this was not written here, but let me add it. So the r that is supposed to be output, okay, has to be returned here. So if I write here return r, okay, then I get exactly this. Okay, so then I get exactly the r that I need in the specification. And if you want to test classical search, so if you want to simply test whether the element y is in the array or not, then you have to test equality with L. So you have to test y is equal to XL. Okay, which by the way that I explained this last time, so at the end of this loop, L is equal to R minus 1. So instead of L, you can also write R minus 1. Okay, so this is the classical. So this is the classical search. Okay. So, but I will use this idea. Okay, I will refer to this idea later. So keep this in mind. I call this this algorithm bean search. Okay, we will need this algorithm later. So now let me delete. So Okay. So and then we said, okay, in a sorted area we can search logarithmically, and then we discussed the problem of uniqueness, which is, this is not the classical searching, but it is very much related to it. So the problem is, if you have a sequence of elements in a set, then decide are two elements equal or not. Okay, and we had two very simple algorithm. The one is the absolute naive algorithm, which simply tests every pair I and j with I less than j. So this has quadratic running time. And then we said that in an ordered array, so if the array is ordered, then I do not need to test every pair I and j, but I need to test only neighbors. So this is some kind of, maybe let me call this here. So I call it no, neighbor uniqueness. So neighbor uniqueness. In this case, I test only two neighbors. If in an ordered array, two elements will be equal, if and only if two neighbors are equal, so I need to test only the neighbors, and then I can reduce the runtime from n squared to n. Okay, and then I also made this remark. I made this remark that if you want to test uniqueness, then it is actually better to use the unique 2 algorithm after sorting the array, because because the time that you need to sort the array, which we'll discuss next time probably. So today I will I will not come to this, but to remind you, I said that the sorting will cost you n log n times log n, not n to the power log n. Okay, so n times log n. And if sorting costs you n log n, then it is faster actually to sort and to run unique 2 than this naive unique 1 algorithm. Okay, so so okay, this was if you have a sorted array. And then we started discussing the problem. Can we do better than n times log n or whatever if the array is not sorted? Okay, and this is what was discussed in this section that I called. Let me call this again. So I called it. I like calling this some kind of database uniqueness. Okay, and the idea in this method was, you are assuming that your set X now is not something arbitrary, but it is a set of integers, a set of non-negative integers, and then you reserve an array with indices 0 to m minus 1, where m minus 1 is the largest integer in this set X, and you use the numbers xn as indices in this array, and you create yourself some kind of database. Was the xn encountered previously among these numbers? Okay, so and then we can you use xn as the index, and if present xn is 1, this means that the xn was encountered for some n prime less than n previously. Then xn is equal to xn prime, so to a distinct, to a equal, and then you can return 0 as is here is requested. And otherwise you record that xn was encountered by putting present xn to 1. Okay, and I said immediate restriction is that m is bigger equal to n. Okay, and again, I think somebody asked me in the chat. So one more time, why m is bigger equal to n? What happens if m is less than n? So so what happens if m is less than n? Okay, then you can simply return 0. So if m is less than n, you immediately return 0. You do not need to do anything because this means you have more elements x1 to xn that are possible values. And when you have more elements which are than values, then obviously some value is repeated. Okay, so this is, I mean, this is not a restriction on the algorithm. Okay, this is not a restriction algorithm, but if m is less than n, then simply the situation is not interesting. You can immediately, if you want, you can put this here. Okay, I mean, put this here. Put this here. So the situation that m is less than n is the algorithm will work, but it is not interesting. You can immediately return 0. So okay, but the problem is that in general you have the opposite situation. So what more commonly happens, and I said this last time. So what happens more commonly is that m is much bigger than n. Okay, so for example, I said if you take 100 machine size integers in C or whatever, then n is 100 and m is 4.3 billion. Okay, so usually you have many fewer elements of the data type than the possible values of the data type. So and then you run into a problem, and then I explain this problem. The problem is that this area is very large. Okay, so this area here is very large, and so this is why you have this very huge memory consumption, and also I discussed this issue of initializing. So initially no xn was previously encountered. This means all the elements in the array present must be set to 0, and this is what is written here. But in practice, when you program this, you have to do this initialization by yourself. So this will run you at the cost O of m. So in fact, this runtime is not O of n, but is O of m. Okay, and now I said if m is large, like for machine size integers, then you have to spend this very long time making this initialization. Okay, and you waste a lot. Not only a lot of memory, but actually a lot of running time as well. Okay, now so we said, and then okay, so this is now some problem. And the next thing that we did is to discuss how to approach this problem. So I want to have an algorithm which is nearly linear without sorting the array, and I want an algorithm which does not consume this huge amount of memory. Okay, so and this is which leads then to this definition, to this idea of hashing. So again, so I mean, this is the most complicated thing that is explained in this section. So I did this once, but once is never enough. So I have to explain this again. So what was the idea? The idea of hashing, and division is essentially so this division. So this division is essentially because I do here my mod p. Okay. So now what is the idea? So the idea is if we go back here, we used xn as an index in this array present, but then present was very big. And now I do not want to have this big array. So this array here should not be in the memory of the computer. Instead, you want to use a smaller array which has size only p. Okay, so from 0 to p minus 1 with indices from 0 to p minus 1. And then you have two problems. The first problem is that you cannot store xn as the index in this array, because there are more possible values of xn than there are elements in the array p. So there are simply too few elements here than the possible values of the set x. So I cannot store the value of some xn as an index. This means I have to store the xn in the array itself. Okay, so this is why I now declare the array, so which I call y, as an integer, not as a boolean. Okay, and I store xn in the array. Okay, so but then so this is the first thing that you have to take into account. And now the other thing that you have to take into account is that okay, so you need to compute some way, so to compute some position where to store the elements xn, and this is what is done by this hash function. So this the goal of this hash function is, when you're given xn, to calculate some place where you try to store the element xn in the array. So okay, this is the calculation of this p. So p, I said p is kind of an entry point, and this is what I tried to explain last time. So now the problem is you cannot use the p directly to store the xn, because there can be different xn's with the same p. Okay, and now you cannot overwrite a previous xn by a next xn, because you need the information of all the xn that you have previously. So you cannot store an xn here unless yp is equal to 0. So we said 0 is kind of 0 is kind of default value for unused entry. And this is also the reason why here we have excluded 0 from the values of the setting. So we are not allowing some xn to be 0. Okay, and then I choose some entry point in by the value of this hash function, and then I go cyclically until I find an unused entry, until I find yp is equal to 0, and then I can put xn there. Okay, and if in the meantime I find some yp is equal to xn, this means that this xn was encountered previously, and then I have two different xn's, and I have to return 0. Okay, and this is the cyclic iterator. So you go up here until you reach the end, and the next element, then you start from the beginning. Okay, so this is how you look for you have to skip and entries with the same value of xn. So, and okay, the memory consumption is O of p. I will say again something about the runtime. I said this last time, but I will repeat. But let us make an example here, which I draw with these graphics. So here is an example of how these elements x whatever are stored in this area of p elements. So when you have a value of the hash function, which is this, then it will start storing all the xli with this value of the hash function, one after the other from left to right here. And then you have some other value of the hash function for some other xmi, then you will store them here. So all these xm1, xm2, xm3, they have the same value of the hash function. xl1, xl2, xl3, they also have the same value of the hash function. Okay? And they are stored starting from this entry from left to right. Okay, so for example, in this example here, let's say I have I put p is equal to 17 and k is equal to 1. I will come to p and k in a moment, but for the time being, just put p is equal to 17, k is equal to 1 in the definition on the previous slide, and then say the hash function is just y modulo 17. Okay, so now you assume that you have some values x li with value of the hash function 0. So these are y modulo 17 is 0. So these are numbers which are divisible by 17. And then when I have these kind of numbers, I have to start them starting from index 0. So 0, 1, 2, and then I put here, for example, 17, 34, minus 17. Okay, because they have rest 0 modulo 17. And I said in this particular case, it's not even necessary to consider positive integers. So negative integers also work as well, as long as they are not 0. So this 0 here, okay, one more time, this 0 here simply means that this entry is unused. It is not some xli which is equal to 0. Okay, so this means I had 3 xli's with phi xli is equal to 0. These are these three numbers, and the fourth number is unused. Okay, so this number here is unused. These three numbers have phi is equal to 0. So, but okay, then you have some other xmi, which for which the hash function has value 6, and then you start storing them here. Okay, so like 6 minus 11, 23, 40, they will be stored from here. And again, 0 is unused, so this means you had 4 values with 4xi with hash function equal to 6. Okay, so now what can happen is you may go over the edge of a region of an empty region. So assume that, let's say, you have 2 xi, so xmi with hash function equal to 3, then it will store them starting with index 3, so 3 and 4. And now assume that you have 4 xli's with hash function equal to 0, then it will start them. Okay, the first one will be stored here, so at 0. Then the next one will be at 1. Then the third one will be at 2. And now, when the fourth one comes, then it cannot store them here. Okay, because there is already something else stored there. This 3 is stored there, and that this is 3 is not overwritten. So what it does is it goes to the right, it goes to the right, and here it has to skip over these 2 elements, and it would put it there. Okay, so you have some kind of a collision of equal values. So this means when you go over this loop, this y p's which are not 0, they will not have the same value of the hash function as xn, not necessarily. So you have this kind of collisions. But and then now let me come to this issue of P and K, because I also received a question in the chat. Somebody was asking me, why does K have to be non-zero, or is K fixed, and etc. So to make this clear one more time, so P and K are fixed. So these numbers are fixed before knowing xn. Okay, so these numbers are fixed before knowing xn, but and this is absolutely crucial. Okay, so this restriction that p is bigger or equal to n is absolutely crucial, because I said if p is less than n and you have all the elements are distinct, then at some point this area here will be full of elements, and this loop will never exit. Okay, so when this array is full, then this loop here, okay, will never exit. So this is why you need p is bigger or equal to n. So this is absolutely crucial. And now about the choice of prime and the choice of k. So I said it is not really necessary that capital P is prime. So this is not necessary, and k doesn't have to be some particular value. In fact, you can choose k is equal to 0. Okay, so this will not make the algorithm wrong. Hey, but why is it written now prime and choose k not 0? And the goal of this hashing algorithm is to have some kind of many different values of this p for different xn. Okay, so if, for example, if you put k is equal to 0, okay, what will happen here? Okay, what will happen here, that you always start at this point. Okay, you always start at 0, and then simply you store the elements one after the other. And then the algorithm is essentially just a copy of the unique one algorithm, of the unique one algorithm, which is very naive and quadratic complexity. So basically, if you choose k is equal to 0, then you give the idea of hashing basically out of your hand. That's what you do. So this way, the goal is to choose k so that different xn have different values of p, as many as possible. And this is why it is good that capital P is prime, because when capital P is prime, every k from 1 to p minus 1 will give you will mix these values very well. So in fact, it is enough, I said. So I mean, it is enough if p and k are relatively prime. This would be enough. This would be enough for a good hashing for a good hashing algorithm. I said also, okay, also a remark. You can choose more fancy hashing function. It doesn't have to be of this sort. Okay. But you must be careful that you do not spend too much time on calculating this hashing function. So the goal here is to have many values, but to be simple to compute, because if this takes too long to compute, you spend more time computing the hash function than actually looking for the duplicates. Okay? This is why, and it has proved that this is this sort of function is the best. For example, you can think about it. I don't want to make a big deal out of it, but so let's say, what happens if you put here +3? Okay, it wouldn't make anything wrong. It will run, but the algorithm would be exactly as good as without the +3. So you gain absolutely nothing from adding here anything. So this will just cyclically permute the entries in the database. So okay. So this means you can try, if you want, you can put something quadratic here. You can say xn times k or whatever. Okay, but it will not make anything better. So okay, this is why this choice of function is okay, is a good choice of hashing function. And now, what would this k do? I mean, what happens if you change k? So maybe this was also asked. So what happens if I change this k? Okay, basically what would happen is this would not really change the algorithm much. The only thing that it will change is it will change these entry points. It will permute them in some way, and these sort of collisions that occur here, like this has to go over that. The number of will change because this piece now will appear somewhere else, and then there will be no collision here, but there may be another collision over there. So this k will not changing this k will not affect the algorithm much. Okay, this is why he wrote, okay, choose it random. Okay? Any k will be approximately equally good, but this is why choose it somehow kind of random. Okay, and then you get close to the best possible. So now we were discussing what is the runtime of that. Okay, and what is the runtime? So the first, something that you cannot avoid is that it is always possible, whatever function you choose, that xn all have the same of value of the hash function. This can always happen. And in that case, this is essentially the same as what I said when k is equal to 0. So then in this situation, all the xn will be stored from here, and then you store the first, then you will go over the first, store the second, go over two, store the third, etc. So what you will get is you will get an equivalent of this unique one. Okay, so you will get an equivalent of this old algorithm. And so this means, okay, so this means, unfortunately, the worst case is, so let me write it here. I can write, so worst case So worst case is not better than the unique one. Okay, so the worst case of the hashing is not better than the unique one, so it is quadratic, unfortunately. So, but then I said, you see, this is only the worst case. In the unique one, essentially every time all the xn are distinct, it will run quadratically. But here it doesn't have to. So what is the complexity? I mean, so you get a complexity. So you get a complexity n from this loop. Let's say when all xn are distinct, you always get this complexity n. But how long does this loop take? Okay, and so what does this loop do? So this loop, if you go here, it is the one which simply runs over this equal with this xli with equal value of the hash function. And in general, there will not be so many. So if the hash function is chosen well and p is sufficiently large, then this loop will run almost at constant time. Okay, so this means the runtime, in worst case complexity is n squared, but in average complexity it will be much less. Okay, and then this also pertains now to the choice of the hash function, etc. So if you choose your hash function, etc., this loop will be short, and then you will not get too much complexity from this loop. So you can almost get linear complexity. So with a complexity which is almost linear, just a little bit worse than linear, you reduce the memory consumption. Right? This was the goal. Okay, and this was the idea of the hashing algorithm. Okay, so so this was about hashing. So now let me try to. I think this is what I finished with last time, more or less. So try to see if I can finish the section. The next thing that we discussed was this order statistics or median value. Okay, and this was if you are given a sequence and you are given a k, then output an index m, so that the number of elements less than xm is less than k, and the number of elements less than equal to xm is bigger or equal to k. Okay, so this is basically saying something like if you are given a number and output an index in this array, so there are a given number of smaller elements and a given number of larger elements. Okay, so sometimes I want an xm where there are few smaller elements and many larger elements, or sometimes I want it the other way around. Okay, and this is what this k kind of captures in this problem. Okay, and now okay, we had two algorithms. The one is order stat1. Okay, now what this does is basically it takes an m, okay, and calculates this and that. Okay, calculates these numbers by simply testing every n. If it is less than xn is less than xm, then it lands in this set. So I augment the size of this n, and if it is less than or equal, then it lands in this set, and then I can augment the size. And if the sizes fit in this way, then m is correct, and I can return it. Okay, and then we noticed that if the array is ordered, then I can simply save myself this whole ordeal, and I can simply return k itself. With now again the remark. Of course, this simple algorithm does not work when the array is not ordered. First remark. And second remark, the output is not unique. Okay, if some xn are equal, then this M may not be unique. So this is also something that you must consider. This means even these two algorithms, they are both correct on an ordered array. They do not need to output the same thing. Okay, so this is so and then and then I come to now. This is, I think, that I didn't manage to do last time. So let me try to explain this uh, range counting. So what is the range counting supposed to? So this is something similar. I'm given a sequence of an array of elements, and I I assume that let's say that the array is ordered. So we assume that this is ordered, and then I'm giving two elements x and x prime, and I want to know how many xm are between x and x prime. Okay, so this is like if you have something like let's say, I mean, so if you have, let's say, real numbers, okay, and then you have, okay, so these are xi, okay, and what you are okay, what you are doing here is something like this. Okay, you're given x and x prime, okay, and you want to count now how many are in between. So 1, 2, 3, 4, 5, 6, 7. Okay, so there are 7. Yeah, so this is what this is supposed to do. Okay, so now let me switch back to. So this is the goal of the goal of range counting, and so what are the possible um, solutions? Just a moment. So okay, so what can you do? And so the first thing you can do is the naive algorithm. The naive algorithm is I simply go through the sequence from left to right. Okay, and whenever xm satisfies this, I count it to the set m, and then at the end I output the number of elements counted. Okay. So this is the naive stupid algorithm, okay, which runs in linear time. And then can we do better? And the answer is that we can, by using that the array is sorted, we can recur this problem to the one that I before marked as bin search. Okay, so if the array is sorted, I know that I can seek an element in the array in logarithmic time with this binary search procedure. Not only seek it, but return. Okay, to return to. So now we had, let me go back. So, okay. So I can find this element r with r is equal to n plus 1 where this is satisfied. Okay, so and then go forward again. I use this algorithm bin search. Okay. And what I do is I simply look up the elements x and x prime in this with this bin search algorithm. So this will, I mean, I do not necessarily want that x and x prime are among the xn, but the bin search will return me this smallest index r. Okay, and I do this now for x and x prime, and then I simply return r minus l. Okay. So I can, and now the complexity of this of this algorithm is O of log of n. Okay, because I okay, this has constant cost. Okay, this simple test here has constant cost, and the bin search algorithm has complexity log of n. So by using bin search, I can improve this range 1 algorithm for a sorted array this way. Okay. So I have then for a sorted array, I can use bin search to have a logarithmic 1D range counting algorithm. Okay, and now to finish, I discuss a version of this, which is of this range counting algorithm, which uses a structure which is called search tree or binary tree. And I think we will talk about this later. Maybe I do not know if it will be part that I will manage, but we will have these trees later occurring in the lecture. And here I will show how one can use these binary trees to get a more or less equivalent but more general algorithm for searching uh, for one range counting and also binary searching, etc. So the idea of this search tree is that instead of storing my elements in an array, so from 1 to n, I use a binary tree, where a binary tree means there is a parent node which is drawn here, and then every node is either a leaf which contains an element of this sequence, or it has two nodes left and right which go down. Okay. So every node except a leaf has two outgoing nodes, so away from the parent nodes. Okay. So, and this is what is called a binary tree. So now uh, assume that you have a structure in which the elements are stored in this way. So this means in every node, all the elements which are reachable from the left are smaller than all the elements which are reachable from the right. So for example, when you are here, on the left you can reach 1, 6, 8, and on the right you can reach 12, 14, 17. Okay. When you're here, on the left you can reach 12 and 14, and when you're here on the right you can reach 17. Okay. So this is, you assume that you have such a data structure. So you have stored your elements in a binary tree which is organized in this way. So this is the first thing that you need. And the second thing that you need is you need your tree to look nice. Okay. And so it's supposed to look something like this, or let's say it should not look too ugly. So what does nice and ugly mean? Uh, you want basically all these leaves, okay, where the elements are stored, to have similar distance from the parent. Okay, so for example, this 17 has distance 1, 2, 3, and this 14 has distance 1, 2, 3, 4. Okay, similarly, 43 has distance 3, and 41 has distance 4. Now it's very easy to see, if you uh, want all the elements to have all the leaves to have the same distance from the root, then the number of elements is a power of 2. Okay, and now obviously it is not the best idea to restrict your algorithm to powers of 2. Yeah, because the number of this n does not need to be a power of 2. Okay, and then you say, okay, you cannot have all the distances, but let's say the distances should differ by at most 1. Okay, and this is what is called, I don't know, I think it's called the balance tree, or okay, some. Okay, and if you have this kind of balance tree, then the depth, so the maximal distance of an element from the parent, is logarithmic in the number of elements. Okay, and so the depth is logarithmic. And now to have an efficient algorithm of how to count the elements between x and x prime, you need to do something else, which, okay, in the beginning, it doesn't look reasonable. And but you will see that it is useful. So what is being done here is that every node which is not a leaf is recorded the list of leaves which are below this node. So for example, this node has 2 leaves, 6 and 8. So and they are recorded here. Similarly here. Now, for example, this node has now 3 leaves below it, 1, 6, and 8, and they are recorded here. And similarly, for example, here, and then this one has now 6 different leaves, and etc. Okay. So assume that it is better in these binary trees not only to sort the elements left and right increasingly, but also in every node which is not a leaf to record all the elements which are below. Okay, so and then how can you count then such a range if you're given such a tree? And now I haven't written, so in this example the pseudocode is not written. The pseudocode is a little bit complicated, but it is a good exercise for you to write the pseudocode yourself if you understand the idea. So the idea is, if you are given elements x and and x prime, you can always test compare. You can compare when you're in this node. You can compare x with the largest element on the left and with the smallest element on the right. And now, here, for example, here you have these 6 elements. The largest element on the left is 8. The smallest element on the right is 12. And now x is less than 8. So this means that x must be somewhere below this node. Okay. And now you again do this. So 1, 1, and 6. Now x is bigger than 1, so it must go to the right. And 6 and 8, and x is equal to 6, so you have to go to the left. And you get the position of the x. Okay. And similarly, you can do here. Now, every time you descend, you can always decide whether a given node is completely contained inside the interval or outside the interval. If it is not contained completely inside or outside, you have to go down. Okay, but for example, in this node, you very easily find that 12 is less than 12 is bigger than x, and 17 is smaller than x prime. This means that this node here is completely contained in the interval, and you do not need to go down here and study what happens below this node. You simply count the number of elements which are in this node to this set. Okay, so this is more or less the idea. Now you have to do this. You have to do this from starting from the parent, and you have to descend. You have to descend every time down. And since the depth of this is logarithmic, okay, the runtime of this algorithm is also logarithmic. So you can locate the position of x in this tree logarithmically, and of x prime as well. And then you have to add the number of elements. In fact, now I mean, an idea is, in fact, if you store the elements like this, then every element, for example 14, okay, is stored once at every level. So 14 is stored once here, it is stored once here, there, it is stored once here and once here. And since you have n elements and each one of them is stored depth of the tree times, and depth is log of n, this means you have all memory consumption or n log of n. Okay, in fact, you can reduce this memory consumption by writing not only the element, not the whole list of elements, but only the smallest and the largest element and the number of elements. So instead of 12, 14, 17, you write only 12 and 17 here and say there are 3. This would be enough. So then you can reduce the memory consumption later, but then the advantage of this is that you can immediately reconstruct a list of xm as well, not only count them. Okay, so you have this method using binary trees, and now of course you need to develop some technique how to create these trees, how to maintain them, etc. For example, how do you insert an element in the array, and etc. And we'll talk about this later. So there will be more algorithmic stuff related to these trees later. And okay, so now one of the advantages of this algorithm, okay, of this approach to range counting is that you can generalize this to 2D. Okay, so now 2D means, let me try to draw it in a so assume that you have not only one coordinate, but let's say you have two coordinates. Okay, so and so you have, let's say, x and x prime. Okay. So you have y and y prime and x and x prime. Okay, and then you have a rectangle in the plane. Okay, and now you have some values of you have some values of some xi, some xi yi. So this is now a point xi yi in the plane, and you have a number of points in the plane. You want to count how many are in this rectangle. Okay, so this is so this kind of rectangular count. So this is a two-dimensional range counting, and now you can accomplish this by generalizing this tree structure by doing now, instead of it's like you have now a tree of trees. So once you have a tree of you have a tree with respect to the x coordinate, and then for every node of this tree in the x coordinate, what stands in this tree is another tree, okay, which is done with respect to the y coordinate. Still in the bottom you have to record both coordinates, but the ordering should be the ordering of the x tree should be with regard to the x coordinates, and the ordering of the y tree, which are the leaves of the x tree, the nodes of the x tree, they should be with regard to the y coordinates. Okay, now there are ways to generalize this algorithm for two-dimensional range counting. So okay, I'm a little bit sketchy here, but okay, okay, so you get the idea of so you have to descend. Now if you're given x and x prime, you have to locate first all the nodes. So for example, when you're here and here, let's say okay, you have to locate all the nodes which are contained in this interval. So this will be this node and this one, let's say, and this. Okay, and okay, so so it is this one. Okay. So and then you have to for these nodes here, okay, you have to apply one more time the search algorithm with respect to y. Okay, and so since descending in this tree is always logarithmical, you will need log squared of n. So for every log of n operations that give you the x nodes, you will need one more time log of n operations to locate the range of the y coordinates. Okay, and then this will give you a log squared of n. Okay, so and I think next time I will maybe do just a little bit of review of section 2, and then we will move to we will move to section 3. Okay, we will talk about sorting. Okay, thank you. This is from me for today. See you on Thursday.
Thank you. And now we're gonna have a quiz. I see that the number of participants is considerably below 300, so that means today attendance counts. And here is the quiz question. Today's quiz consists of 3 questions, and each question is a single choice. Question A, what is the purpose of algorithm design? And there are 4 possible answers. Please write in the chat which answer you choose. And same for question B, what is true about neighbor search? 4 possible answers. Please choose which answer or which answers, possibly several of them, right? And question C, what is a necessary condition for the construction of the hash function so that the algorithm terminates, right? So in the lecture, we have had one particular hash function that involves prime numbers k and p, and as Alexander pointed out, not all of these conditions are necessary. Which of the following conditions 1, 2, 3, 4 are necessary so that the algorithm terminates? And you have got 15 minutes